Now that we've covered the issue of bond polarity, we're ready to look at molecular polarity. So what we're going to do is we're going to look at how bonds are polar or not, and how those polar bonds can contribute to a molecule being polar or nonpolar. We'll start with this example, or I should say these two examples here. I'm going to look at water, and we're going to look at carbon dioxide. And I've drawn the Lewis structures for both molecules, ignoring lone pairs, here for water and here for carbon dioxide. Now in water has two OH bonds. And so we're going to want to look up the electronegativity for oxygen and the electronegativity for hydrogen. And if we look those up, we're going to see that hydrogen has an electronegativity of 2.1. And oxygen has an electronegativity of 3.5. The difference there is 1.4. And so any OH bond is going to be a polar bond with a pretty large difference in electronegativity of 1.4. And so the dipole moment is going to point from oxygen to hydrogen, where in this OH bond, the oxygen is going to be a little more negative and the hydrogen is going to be a little more positive. We can do the same thing over here for carbon dioxide. We're going to look up the electronegativity for oxygen. Well, we've already seen that's 3.5. And the electronegativity for carbon, that's 2.5, for a difference in electronegativity of 1.0 between carbon and oxygen. And so if I have a bond between carbon and oxygen, a dipole moment is going to get set up, and that dipole moment is going to point from the more electronegative atom to the less electronegative atom, so from the oxygen to the carbon. And our oxygen is going to be a little more negative, and our carbon is going to be a little bit more positive. And so we see that both water and carbon dioxide have polar bonds. And yet, remarkably, water is a polar molecule, whereas carbon dioxide is a nonpolar molecule. What in the world's going on here? How can a molecule that has, in a sense, two polar bonds, right? We've got one here, and we've got one here. If we've got two polar bonds in the molecule, how can it be that the molecule overall is not polar? Well, it's important to recognize that these things that we're drawing here, these little arrows that look like this, they are what are known as vector quantities. Vector quantities. And a vector has, in addition to a size, so vectors have size, but they also have direction, and you have to include both of them. So in normal math, you're used to, say, if I'm going to add two numbers, like a 5 plus a 1, we just add them together. Well, with vectors, you have to consider not just adding the size, or sometimes they call it the magnitude, but also the directions. So for example, here's how this works. We're going to go ahead and we're going to, let's just make a XY axis here, and here's my origin, okay? And we are going to take a vector and we're going to point it in this direction at 45-degree angle, this way. And we're going to say this vector here has a magnitude, we'll just call it, we'll call it 1.4. And I'm going to call that 1.4 because that's the difference in electronegativity between hydrogen and oxygen. And then we'll go ahead and we'll point another vector in this direction, in the opposite direction, where it makes a 45-degree angle with the negative side of the x-axis. And we'll also give this a value of 1.4. Now, if we add these two vectors together, they're pointing in opposite directions, and they have equal magnitude. When that happens, they cancel out. And overall, we would have no vector left over. So we're going to have to remember this when we're adding vectors. We not only want to keep track of how big the vector is, but also in which direction it's pointing. And this just keep this idea in mind when we're thinking about molecular polarity. So let's go back to our water molecule and our carbon dioxide molecule. And we're going to go ahead, we're going to do carbon dioxide first. So I'm going to go and I'm going to draw an XY axis here like this. All right? And then I'm going to imagine, let's see, the difference in electronegativity between carbon and oxygen. That was 1, wasn't it? That was 1. So what we're basically going to have here is this is going to point from the oxygen to the carbon with a value of 1, because that's the difference in electronegativity. And then this one's going to point from this oxygen to this carbon with a value of 1. And if we sort of draw that here on our axis, that's going to go right along the x-axis. We're going to start here at 1. We're going to make this, the length of this vector 1.0. And you know what? We're going to do the same thing over here on this side. This would represent the position of the oxygen atom, the carbon atom, the oxygen atom. And this distance here is also 1.0. These are pointing in equal and opposite directions. So while they both have a value of 1.0, those vectors that result from the bonds in carbon dioxide, you have one vector quantity pointing from left to right, another vector quantity of equal magnitude pointing from right to left. They cancel each other out. And this is something we're going to have to keep in mind for molecules if we have vector dipole moments, such as we do for carbon dioxide, and those vector dipole moments point in equal and opposite directions. That polarity in each bond cancels out, making carbon dioxide nonpolar overall. Now, if we try to do the same thing for water, we're not going to get the same result. Okay, so let's look at this. The difference in electronegativity is 1.4. So we can think of drawing vectors from the more electronegative atom to the less electronegative atom. And we're going to think of these having a magnitude, a size of 1.4 each, like that. And if we're sort of drawing our axis, like this, we can imagine our oxygen sitting here, and then we're going to have vector quantities pointing from the oxygen to the hydrogens with a magnitude each of 1.4. Of course, these are going to be 104 degrees from one another, because that's the bond angle in water. In this case, our dipole moments do not point in equal and opposite directions. I mean, they do along the x-axis, right? There's a component this way that cancels out a component this way. But there's a component pointing downward that is not canceled out by anything moving upward. And because of this, a water molecule actually has a net dipole moment that looks like this. Just points straight down. The sideways stuff, that gets canceled out, but the straight down pointing does not. And so water actually has what we call a net dipole moment, and it is a polar molecule overall. Now we can extend this to some other molecules. It gets a little tough. It actually gets real tough when you're in 3 dimensions, but we're going to just stick to 2 for now. But let's imagine the molecule boron trifluoride. Now you got to be careful here when predicting whether molecules are polar or not. You got to get the geometry right. That should make sense. And if you go through the Lewis structure for boron trifluoride, which I've drawn here, you're going to actually find that boron trifluoride is a trigonal planar molecule. So its orientation, atomic orientations are kind of like this, right? All of the atoms lie in a plane with all of these being 120 degrees from each other. Okay? So while I may have drawn the Lewis structure like this, you better recognize that I need to know what the actual structure of the molecule is and try to indicate that as best as I can. In this case, 120 degrees, 120 degrees, and 120 degrees. So there is a difference in electronegativity between boron and fluorine. So fluorine has a dipole moment of 4.0, and boron has a dipole moment of 2.0. So the difference in electronegativity between fluorine and boron is 2.0. And so I can draw in vectors along this Lewis structure that are going to run from the more electronegative element to the less electronegative element, like this. And I could take you through a mathematical description of this if you would like. I hope you will trust me when I tell you that if I have a trigonal planar arrangement of identical atoms, all three fluorine atoms, around a central atom, any dipole moments that exist are going to cancel each other out. And so boron trifluoride, BF3, is actually a non-polar molecule. However, if we were to do something like this, where we're going to replace one of the fluorines, say, with an iodine, then we've got an electronegativity of 4.0 here. We got an electronegativity of 4.0 here. We got an electronegativity of 2.0 for boron, and we have an electronegativity of 2.5 for iodine. Then we have a difference in electronegativity along this bond of 2, along this bond of 2, and along this bond of 0.5. And so when we lift the symmetry, we make one end of this sort of triple bonding around the boron. When we make this one a little weaker, it actually turns out that BIF2 is going to be a polar molecule. And this happens a lot when you lift the symmetry around a particular molecular geometry. Let's look at another example. The other example we'll look at here is chlorine trifluoride, ClF3, which has a Lewis structure that is T-shaped. So I am drawing this geometry appropriately here. If you run through the Lewis structure, you will find that ClF3 is T-shaped. We know that the electronegativity of fluorine is 4.0. and the electronegativity of chlorine is 3.0. So we have a difference in electronegativity of 1.0 along all three of these bonds. The dipole moments that result in each bond are going to point from the more electronegative fluorine to the less electronegative chlorine. And we're going to ask ourselves, what do these vector quantities do? Well, I hope you see that the two running along this direction, they cancel each other out. So in a sense, I could just ignore these thinking polarity-wise. Here then, we have this portion of the dipole moment that clearly survives. There's nothing pointing down in the opposite direction to cancel this out. And so chlorine trifluoride is a polar molecule. This gets a little tougher. Sometimes you're going to have to think of this in 3 dimensions, such as the case with ammonia. You might remember that ammonia is a trigonal pyramidal molecule. And so in ammonia, we have a nitrogen atom that sits up at the apex of a pyramid. So this nitrogen atom is sitting up above the plane of the paper that I'm drawing on. And the nitrogen has an electronegativity of 3.0. In the plane of the paper, we have 3 hydrogen atoms, all of which have an electronegativity of 2.1. So the difference in electronegativity along this bond, along this bond, and along this bond is close to 1 at 0.9. And so we have dipole moments that are going to be pointing from the nitrogen down to each hydrogen with a relative strength of 0.9. Now we can sort of see that in the plane of the paper, the dipole moments cancel out, but there's a downward component pointing from the nitrogen down to this hydrogen, down to this hydrogen, and down to this hydrogen that is not offset by anything up above the nitrogen. And so because of this, ammonia, which is a trigonal bipyramidal molecule is going to be a polar molecule with a net dipole moment. Let's see, it's going to stick in this direction, right? It's going to stick downward. There's a downward component through the nitrogen that is not offset by anything up in the opposite direction. Let's look at the other possible molecular geometries. We have tetrahedral, trigonal bipyramidal, and octahedral. And I'll draw representations of each of these. Let's see, we'll have methane, which could be represented like this. In the trigonal bipyramidal arrangement, we could have phosphorus pentachloride with a phosphorus in the middle and all chlorines around the sides. And for octahedral, we could have sulfur hexafluoride, which can be represented like this. The sulfur in the middle, and this would be PCl5. If we have a tetrahedral arrangement like this, where all positions on the tetrahedron are occupied by the same atom, it turns out that any polarity that exists in any bond is canceled out. That's so long as all positions are identical. So in methane, you have a difference in electronegativity between the central carbon and the hydrogen, but it ends up that the bond orientations end up canceling out through this vector addition. It cancels out any polarity that exists in the bonds. And so methane is a non-polar molecule. In the trigonal bipyramidal arrangement, once again, so long as all positions are occupied by the same atom, such as we see in phosphorus pentachloride, what we're going to do here is we're going to look at the axial positions. Those axial positions actually end up pointing in equal and opposite directions. And so in a sense, they cancel each other out because, if the electronegativity is running this way, then they're pointing in equal and opposite directions. And if they're pointing this way and this way, they're pointing in equal and opposite directions. So we can pretty much ignore any polarity that exists in these two bonds, and I'm ignoring them symbolically just by removing the atoms that would be located there. And then what we're left with, once we do that, we're left with the trigonal planar arrangement, which we showed earlier, that if these are occupied by identical atoms, that the polarity cancels out. And so a trigonal bipyramidal arrangement, where all of the atoms are identical, would also be nonpolar. And if we go to the octahedral arrangement, such as exists in sulfur hexafluoride, such as this, all of the positions have a partner pointing in an opposite direction. It's actually easier, I think, to see it here. In an octahedral arrangement, what we sometimes do is we draw 4 positions around the central atom as sort of a hatched square, but this is an actual square arrangement. So we can stick the 4 fluorines in the square plane around each other here. And then there's a position that goes directly up above the plane and directly down below the plane of the square. And remember, all positions in an octahedral are identical. It should make sense, the polarity is going to run this way. It should make sense that up and below the plane of the paper, those dipole moments are going to cancel each other out, again, as long as these are identical atoms. And if these are identical, then these two are going to be showing the same effect. And these two will cancel each other out, and these two will cancel each other out. And so we would expect sulfur hexafluoride also to be a nonpolar molecule. But you're going to have to remember this idea that this is only true if all of the atoms surrounding the central atom are identical. And it can get tricky. I'm going to throw a couple tricks at you here. But let's just, for example, let's just start and say, let's say instead of sulfur hexafluoride, we're going to have something that looks like this. We'll have a central sulfur, and we'll put fluorines all around the square and the plane with the sulfur. And then sticking up here, we're going to put another fluorine, but sticking down here, we're going to stick an iodine. Well, this would be a polar molecule. I hope you recognize that. Now, it would be the case that any dipole moments in the plane are going to cancel each other out. And if this was a fluorine, this would cancel out any dipole moment pointing down in this direction. But the issue here is that the difference in electronegativity between iodine and sulfur is different than the difference in electronegativity between fluorine and sulfur. And because of that, this is going to have a larger difference in electronegativity, which would end up being 2.0. And the difference in electronegativity between sulfur and iodine is actually 0. And so in a sense, there's nothing opposing this dipole moment in this direction. And so this substance, SF5 with an iodine, would be a polar molecule. All right, let's try to trick you here then. What do you think this one's going to be? All right, we're going to put 4 fluorines here. And in this case, we're going to stick an iodine here, and we're going to stick an iodine here. Polar or nonpolar? I hope you guess nonpolar. With all of these canceling out in the plane, this cancels this cancels this, and there's nothing here and nothing here, so there's no dipole moments to worry about. And if there were dipole moments, let's just say there are, pointing from iodine to the sulfur, because they're identical atoms at opposite positions, those would cancel out as well. I'll give you one more to think about. Let's do a trigonal bipyramidal arrangement. We'll do 2 different ones, maybe 3, we'll see here. See, we'll do PCl3I2. So here we got a central phosphorus here and here. And here we're going to put our chlorines here, here, and here, and our iodines here and here. And in this case, we'll put our chlorines here, here, and here, and our iodines here and here. What do you think? This case would be nonpolar, with all positions, all equatorial positions are going to cancel each other out in the trigonal planar plane, and then the 2 iodines sticking up and down would cancel each other out. Here that symmetry is lifted, and this would be a polar molecule. This would be a polar molecule because you don't have that balance in this particular molecule that you do in this one. So even though both of these structures, they have the same molecular formula, PCl3I2, they're actually different molecules with different properties, where one of them would be polar and one of them would be nonpolar, and these are considered isomers of one another. Isomers are substances that have the same molecular formula, but they're different structures. They're different orientations of the atoms in space. I'm going to leave you with one more here. What do you think of that? I hope you recognize that this one's going to be, I almost said nonpolar. This one's going to be polar.